everyone, and welcome to the 65th session of the Porous Media Tea Time Talks. My name is Catherine, and we have two brilliant speakers joining us today, Weipeng and Nathan. And we're going to start by introducing Weipeng and his talk. So, Weipeng is a postdoctoral associate at the University of Minnesota. His research focuses on the effects of fluid flow on mixing, reaction, and mineral precipitation in fractured and porous media. So, Weipeng, I'm going to hand over the stage to you.
Okay. Yeah, thanks, Catherine, for the introduction. Hello, everyone. Today I'm going to present fluid inertia control, fluid mixing, and mineral precipitation in fractured and porous media. So, mixing-induced precipitation in fractured and porous media is a critical process that controls many subsurface applications, such as carbon mineralization and enhanced geothermal energy recovery. And subsurface formation mostly highly fractured. So the fractures are high wave for fluid flow, and fracture intersections are the reaction hotspots. And so the typical flow rate in the fracture can be high enough to induce inertial flow, which can dramatically alter the flow topology and change the flow and transport dynamics. The previous study on mixing-induced precipitation mainly focused on the creeping flow condition. So as we can see here, the mix of two reactants will lead to formation of a very thin layer along the mixing interface. But the effect of the fluid inertia on the mixing-induced precipitation hasn't been explored. And our previous study has shown that the fluid inertia can fundamentally change the dynamics of mixing-induced homogeneous nucleation reaction. As we can see from these two plots, these are results of a chemiluminescence experiment. So basically, when the two reactants are injected and when they mix and react, they will emit light. So what's captured here is the light intensity. So for the low risk number, you can see there's a sharp front, and that happen at the mixing interface. But when the risk number increases, we can see the reaction dynamics changes dramatically. There's a emergence of second reaction stream. This is because of if you take a look at streamline, you can see there's a more complicated streamline. There's also this kind of vortex that significantly enhance the homogeneous reaction. But for the precipitation, as a heterogeneous reaction, in which the access of the reactant to surface is critical, so which make it fundamentally different from the homogeneous reaction. So our goal is to review how the inertial effect can control the mixing-induced precipitation and clogging in fracture and porous media. So to study this, we did both microfluidic experiment and 3D reactive transport simulation. So for the microfluidic experiment, we used two minerals. One is the barium sulfate, the other one the calcium carbonate. So for the experiment, we used two pumps to inject these two solutions into a microfluidic chip. Then they will mix and then precipitate. And for the numerical simulation, for the flow field, it was solved by it was obtained by solving the continuity equation and Navier-Stokes equation. For the solute field, it was obtained by solving the vector diffusion equation. So for the precipitation, we modeled it at the surface reaction. So the reaction was used transition state theory with the first order kinetic model. So here, first we studied the equal injection rate condition. And so for the low risk number, as the reaction happens, it will form this kind of very thin precipitation barrier along the intersection and then extend it to the downstream. So this is similar to people observe under creeping flow condition. But as the risk number increased, you can see that the precipitation was enhanced significantly. So you can see that the width of precipitation at the intersection become much wider, and also similar for the precipitation in the downstream. And for the highest risk number, we saw a significant enhanced and very localized precipitation that occupy almost the entire intersection. So this result indicates that the fluid inertia effect can fundamentally change the spatial precipitation pattern. So to understand how the fluid inertia changes the precipitation pattern, here we show the streamline and surface direction rate at the intersection. So color of streamline indicates their z location value, and the color on the surface indicates the surface direction rate. So here you can see that for risk number 10, the streamline essentially two-dimensional. They are smooth and parallel to each other. So because of this kind of streamline, here we show the distribution of the supersaturation at this coupling. So you can see that because of this kind of streamline, the solute, the supersaturation only localized at the mixing interface because the surface direction. So the precipitation only happen on top and bottom surface as a supersaturated region. But this is not the case for the high risk number. For high risk number, you can see that there's a dramatic change in the streamline topology. So the streamline is three-dimensional. It comes from center of the channel, and then they divert after they hit the mixing interface, and then they travel along the top and bottom surface. So that's why it will lead to. So from the cross section, we can see that because of this kind of unique flow topology, it brings the supersaturation to the top and bottom surface. So that's why it leads to very significant enhanced precipitation occur almost at the entire intersection. So this kind of different precipitation pattern can also lead to different clogging behavior. Here we measure the change of the conductivity of the channel at different risk number. So you can see here for low risk number, initially there's a slight decrease in the channel conductivity, but then later it will reach a plateau. This is because of this kind of thin precipitate is grow vertically, and then finally it will form an impermeable wall that can stop the further mixing and precipitation. So you can see from the right figure, after this kind of wall form, we only inject fluorescent tracer from the left side. For the right side, there's no flow, it's stationary, but still, you can see after 5 minutes, there nothing can go to the right side. That indicates that this kind of layer is impermeable. But but in contrast, for the high risk number, we can see a very fast, dramatic decrease in the conductivity because of this kind of significant enhanced localized clogging. So here we want to examine how the symmetry breaking can affect the precipitation pattern. So here we increase the flow rate from the left by 20% to induce a symmetry breaking. So for the low risk number, the streamline we can see that because from the left there's higher flow rate. So the streamline from the right from the bottom can only go to the right. So that's lead to the initial precipitation only happen on the right channel. But later, when the permeability of this channel decreased, then the precipitation can happen simultaneously in both channels. But that's intuitive. But what's interesting is for the high risk number, you can see here, although the flow rate from the bottom is slower, but still we can solve this kind of flow bifurcation. The flow can effectively enter both downstream. So that can lead to a simultaneous enhanced precipitation in both downstream channels. You can see from the video. Yeah, that's lead to enhanced precipitation both in the downstream and also at the intersection. So now we already know how the fluid inertia affect the mixing precipitation at a single intersection scale. So we want to see how it behaves in a larger network scale. So we design this 3x3 network and do the experiment at both low and high flow rate. So what we observe is similar. At low flow rate, there will be formation of this kind of thin barrier, but for high flow rate, you can see a very dramatic precipitation across the entire network. That lead to a significant clogging. So that means our results can successfully be translated from single intersection scale to a network scale. And also the inertia effect is even more dramatic at the network scale. Here we also show how the conductivity change. You can see that for the high risk number, we can saw even faster decrease in the conductivity. So now we know how it behave as a network, how the fluid inertia behave as a network. So we want to extend it to porous media. So we want to examine how the inertia and symmetry breaking can affect the fluid mixing and mineral precipitation in porous media. So we designed two different porous media. One is outer porous media. So in outer porous media, everything is symmetric, so the symmetry is preserved. You can see here, by increased release number, it can only slightly enhance the local fluid mixing, but it cannot enhance the like a global fluid mixing. But in the disorder porous media, low release number only with the symmetry breaking, there's no enhanced mixing. But when we have both fluid inertia and the symmetry breaking, we can saw there's a very significant enhanced fluid transverse mixing and dispersion. We can also see there's lamellar structure and the recirculating vortices. So that also indicates this process is chaos. So to understand the porous-scale mechanism, we run the flow simulation in this kind of a unit periodic domain. So we vary the angle of the body force to see how the fluid inertia and symmetry breaking affect the mixing process. Because for this kind of geometry, so for 0 degree and 45 degrees, it's symmetric. So for the angle in between, it's symmetry breaking. So here, first we show the streamline low release number. You can see here for low release number, the streamline is smooth and parallel to each other. So they are initially 2D. So even there's a symmetry breaking, you can see that the streamline is still confined with their own flow path. It cannot go to the other side. But when we have fluid inertia, you can see that for the symmetry case, although there's fluid inertia, but still, although there's some like inertial structure like this kind of recirculating flow and also de-flow, but still the streamline cannot go to the other side. Actually, the streamline here is artifact, it's not real. It cannot go to the other side. There's a mixing barrier. But what's interesting for the symmetry breaking case, you can see that although the main flow direction is to the right, but still you can see some streamline can go transversely to the left side. So that leads to the global enhanced mixing. So finally, we want to examine how this fluid inertia can control or enhance mineral precipitation in the disorder porous media. So here we co-inject calcium carbonate into the microfluid chip. So for release number 1, we can saw there's a formation of this kind of thin precipitation layer. Similar to previous study, it will go vertically and then finally it will form a wall. But for the high risk number, we saw quite different, very dramatic enhanced transverse precipitation. So conclusion, fluid inertia is critical in controlling mixing the precipitation and clogging in important network scale flow. And the fluid inertia and symmetry breaking can lead to global chaotic flow and widespread mineral precipitation in porous media. Yeah, I think that's all my presentation. Any questions?
Great, thank you for that. That was really interesting. So if people have any questions online, you can basically type them in and we can read them out. But I was going to start with a question that I had, which was, so during my PhD research, I was looking at a fluid flow phenomena called intermittent pathway flow, where, you know, the non-wetting phase or like the gas would periodically connect and disconnect. And I really struggle to ever recreate that dynamic in micromodels because of the lack of like 3D connectivity. And so do you think that your work is going to be easily translatable to these 3D porous medium, or do you think you're going to have to include more physics when you introduce that extra third dimension of connectivity?
Yeah, actually, I think it can be because actually 3D-dimensional flow is even more dramatic in the 3D porous media. 3D fracture. Yeah. I think and also there's already some like numerical simulation that is the exam stream. What does stream look like at 3D fracture intersection? Actually, it's quite dramatic. So I think if we include mirror precipitation, it's still gonna be very important in 3D systems.
Yeah, I think it's going to be very important. And I think I've seen a talk at Interpor previously where they were struggling to get the hexagonal precipitation shapes that you see in, say, like Death Valley with just 2D simulations. Like they had to add in that third dimension of connectivity.
Yeah, that's true.
Is that something that you want to do for your future research, or you still have other like unknowns for your 2D micromodels?
Yeah, 3D. The problem of 3D is actually I think because they are doing simulation, right? But for experiment, even it's quality 2D porous media, but actually the growth is still 3D.
Yeah.
But I think if we, of course, it's ideal if we can use the 3D porous media, that would be ideal. But the problem is the visualization. Cannot use the microscope to visualize it.
It's difficult. Yeah. Great. Well, thank you so much, Weipeng. And I'm going to go on to our second speaker of today's session, which is Nathan. And so Nathan Jones did his undergrad at the University of California, Santa Barbara, and is now fourth-year PhD at Caltech, working with Professor Ruby Fu in mechanical and civil engineering. He studies systems involving ice-water interactions from sub-millimeter scale to multimeter scales with both numerical and experimental techniques. And so with that, Nathan, I'm just going to add in your slides, and the floor is all yours. Oh, let me just unmute you as well. Great. There you go.
We're good? Okay. Great. Thank you so much for that introduction, Catherine. Yeah, I'm excited to talk about some of this work that I've done. I know in the introduction it mentioned numerics and experiments. This is all numerics today. We can maybe talk about experiments if there's a question, but in terms of concrete results, not too many of those yet for experiments. But yeah, let me just jump right into this. So really, to kind of set the scope of what this problem is, we're looking at this sort of centimeter scale phenomena, specifically of water infiltration into dry porous media. And so this picture at the top left by Glass and Nicol are these classic experiments of these dry glass bead packs in which they infiltrate water on the top. And they observe these fingers that form with this water. So the color bar here is, I believe, just saturation due to light intensity. And so this is ubiquitous across unsaturated porous media. This happens in glass beads. This is an example of more experiments done more recently in sands, in which they vary the properties of the sands here. I believe this is the grain diameter. And then, of course, in unsaturated snow, in which they have these sort of, in the field, they do these, like they dig a snow pit and then pour this red dye over a section of that and then cut through. And we can see the formation of these preferential flow pathways and these sort of lateral barriers as well, which is a characteristic of snow. And so physically, this instability occurs due to that local competition between gravity that drives the liquid water downwards and capillarity and surface tension effects that resist the flow and that form these very evenly spaced, evenly thick fingers across these systems. And so for the purpose of what I'm going to talk about today, we only are interested in this icy porous media or snow or fern or whatever you want to call it, which now we can have the added effects of heat transfer and phase change. And so because snow exists below the freezing point of water, because it is frozen water, there's now this sort of temporal heat transfer and phase change that can occur. So in the field, these sort of excavated solid ice pipe structures have been observed. So this is an example, I believe in terrestrial snowpacks, I think in Canada, and these two are both in Greenland, of these snow pits that they brush out this porous snow, and that these solid structures are left behind. And so these are sort of evidence of freezing or refreezing that occurs due to this snow melt that occurs in these preferential flow pathways. And so these sort of solid skeletons that exist in the snow are going to affect things like the bulk hydraulic properties, the thermodynamic properties, because we're now introducing heterogeneities, which the porous medium will now become anisotropic due to these sort of long, slender bodies that are in the porous medium. And also, when this refreezing process occurs, because there's this local latent heat exchange, that'll affect the local energy balance, and we'll see local warming events when these sort of structures are formed. And so really, we're interested in developing an understanding of how these structures are formed in these porous snow systems, and then also looking at how these structures influence the infiltration dynamics of this gravity-driven flow in these porous ice systems. And so we do this primarily right now with the numerical simulations. So I'm going to briefly just run through the model, and we can get into some of the results here. But so we utilize a Darcy scale flow model in which our domain consists of solid ice, air, or liquid water. And the four main variables that we track here, or the four unknowns, are just the porosity, which relates to the ice mass in the system. So if this decreases, right, we would see freezing, the liquid saturation. And then what drives the phase change in our model is the fact that we have local non-equilibrium in thermodynamics. So we segregate the temperatures into the ice phase temperature and the water phase temperature. And the difference in these temperatures is what drives the kinetics of the phase change. So again, to just briefly run through the model equations, I guess the more important takeaway from this slide as I go through everything are the relevant non-dimensional groups. And so if we look at the ice and water mass phases, these are just simple reaction equations, right? If you're not familiar with the Domkeller number, it simply is the rate of phase change over the rate of advection, but I'm assuming most people in the audience are very familiar with this. The Stefan number is the ratio of sensible heat to latent heat. Really, in our problem, it's only a function of the initial ice temperature, or how cold the system is initially. The energy conservation of each phase, again, are these familiar advection diffusion reaction equations, which now we can now introduce the Peclet number here. And our flow velocity is based on this unsaturated phase field model. Phase field model of unsaturated flow from these two references here, in which this is a natural extension of the Richards equation by doing a second gradient extension of the capillary pressure curve. But really, that's it. The main purpose of this slide is to sort of highlight what relevant non-dimensional groups there are once I talk about analysis. So an example of what this model output would look like is if we consider this system. So this is a 1 meter by 2 meters to give you the sort of length scale here. Initially dry, or saturation here is close to 0. Initially homogeneous in porosity, which is a okay assumption. For now, we're just kind of demonstrating the baseline of this model. Initially, everything is at minus 10 degrees Celsius for the ice temperature, and the water temperature initially is just at 0 because we're assuming it starts at equilibrium. And so we're just going to infiltrate water at the top at a rate of 18 millimeters per hour. And when I play this video, if you look at these sort of first two movies, I'll play it now, we see the development of these fingers as the water propagates downwards. Again, as I mentioned before, with porosity, anytime you see decreasing, that's local freezing. So we're adding to the ice matrix here. And between ice and water temperatures, you can see this subcooling at the furthest wetting front, which is where most of the phase change is occurring. And behind that, most of the system is now at equilibrium, and there's no more phase change happening. So we see the development of these sort of ice pipe-like structures in which most of the freezing is occurring at the macroscopic ice wall interface as they progress downwards. So these pipes aren't fully frozen. The porosity is significantly decreased, but we can still allow flow in this region. Like you can see, there's still saturation that penetrates downwards in them. But a lot of that water mass is being lost to ice during this freezing process. Just looking at some kind of more analytical results here, if I just showed you this sort of slice here, if our initial snowpack temperature was say -10, if we look at the liquid water and the porosity here, if we just simply vary what the initial snowpack temperature is, of course, with these really harsh, really cold simulations, we would expect to see more freezing, so a higher magnitude of this sort of darker color. And if we take an isothermal system, of course, we wouldn't see any freezing at all. And so just varying one parameter here, which is the initial temperature, we can see that decreasing that initial temperature will make this melt infiltration depth more shallow. I should mention all of these screenshots are taken at the same time. So for the same elapsed time with colder temperatures, we'll see a overall average slowness of the infiltration frontier. And this is primarily due to two factors. The first is simply that when we convert water to ice, there's a mass loss of water, so the amount of water for transport will be reduced. And the second is the fact that because we're freezing and we're decreasing the porosity, the effective Darcy velocity in these regions will be slower. So the overall infiltration rate will just be slower. And so the other thing we can vary here is the infiltration rate. So if I just plot it, I'm just plotting the infiltration depth after around, I think, 3 hours of simulation time. X-axis is the same with initial snowpack temperature. And here we're just plotting the infiltration depth for a family of curves of different initial snowpack temperatures and increasing melt water flux rate U. And so we get these sort of similar behavior. Of course, with colder temperatures, we're going to decrease the infiltration depth. And with more mass flux, we would expect the infiltration depth to be higher. But here, if we sort of non-dimensionalize things and use this Domkohler number, we can see that this behavior collapses fairly nicely. And this normalized infiltration rate is just this value over the infiltration rate. So the value here of 10, for example, means that the actual infiltration rate of the wetting front is 10 times faster than the water melt rate you're supplying, for example. But here, this kind of reveals that below a certain threshold of, say, Domkohler 40, the rate of phase change and the advection effects are in much stronger competition, both because the slope is sharper here, but because there's a bit more variability. Where after this, we kind of are in this really high phase change rate regime, and the flow behavior is mostly just controlled by the amount of freezing that's happening. The second thing that I want to point out about this problem, specifically this sort of gravity fingering problem, but in snow, is that in the sort of classical literature here, if you can see, I hope this shows up well. This again are these classical experiments of water infiltration in dry glass beads. And you can see that each of these fingers, this darker shade region is the future of these experiments, is that each finger just simply keeps propagating downwards. There aren't the development of new fingers in between here, just whatever fingers exist are going to keep propagating. But we find that with the introduction of phase change, that isn't necessarily true. And so here's the start of a simulation. And if I play this video, you can see that in between these sort of primary fingers, that these new sort of secondary fingers, as we call them, pop up. And so again, just for semantics, those initial fingers here, which you can see most of the phase changes happening, are what we call the primary fingers, and these new sort of ones that happen after the fact are what we denote the secondary fingers. And so why might we care about this? Effectively, what secondary fingers do is reduce how channelized the flow is. So if we initially have 5 fingers, if these were to keep propagating downwards, we would expect much faster infiltration depth as opposed to, say, stable flow. And also the flow is much more localized in only these 5 fingers. But as time goes on, we can see that if you take a cross section here of saturation, the flow is now much more evenly distributed in the domain. And it also has the effect of slowing down the overall flow. So here I'm just showing that these secondary fingers only form in these regions of thermal equilibrium in which it doesn't have to combat this new phase change and this new decrease in porosity to form. They can form in these like easy, nice regions of flow in this thermal equilibrium. And the black dotted line is the front of these secondary fingers. And they quickly catch up to the wetting front of the initial fingers. So if you look at the velocity profiles here of the average finger velocity in these simulations, when the secondary fingers form, they initially shoot up in velocity. They propagate much faster than the primary fingers, and they also decrease the effective infiltration rate of the primary fingers by quite a bit, almost by half here. And so to sort of quantify the reducing channelization effect of the secondary fingers, here I'm just plotting the variance of saturation for two example simulations. Again, Stefan number is just related to the ice temperature, so a higher Stefan number would be a colder initial simulation. So here you can see with this darker curve, this sort of lower Stefan number, this doesn't form secondary fingers. These initial channels just keep propagating downwards. It's very similar to the classical case of water over glass beads. But in this lighter green simulation, we start off not forming secondary fingers, but at around 100 minutes, these secondary fingers start forming and the variance drops sharply. Despite this one runaway finger, you can see that more of the x-axis here is saturated in the main sort of wetting front, whereas here the flow is still very highly channelized in these initial flow fingers. And so just to summarize, so here I'm plotting Stefan number, again, relating to ice temperature, and y-axis is the Peckley number. If we plot the results here in which we do see secondary fingers and which we don't, so we just see these initial fingers that keep propagating, we notice that the secondary fingers only are showing up here at rates of high Stefan number and high Peckley number. And we theorize that this is due to these sort of two compounding effects. So for secondary fingers to form, you have to both have sufficiently high freezing for the system to now energetically favor the flow, looking for these new nice thermal equilibrium regions to open new pathways. So that would be increasing Stefan number. But then also you have to have enough liquid flow being provided to these regions to then drive the flow into these new thermal equilibrium regions. And so that would be increasing Peckley number. And so if we plot this sort of isoline of this product of these non-dimensional numbers, we can see that there's some threshold here. It's 1e-4, which above this we see secondary fingers, and below this we just see the primary fingers. And then again, this sort of bottom right here is when the flow is so high, or sorry, the initial temperature is so high compared to the flow that we don't see any flow at all. Here we just see complete arrest of the flow. And here we find that isoline is around Domkohler here, around 670. But so here we can see these sort of three regimes of behavior where you either don't have any flow, and any flow that will be completely frozen, will form this impermeable layer. This region of where you see this sort of fingered flow that keeps propagating, as you would expect in the classical experiments. And then this high Peckley times Stefan regime, in which you do see fingered flow, but also the formation of these secondary fingers. And so I'm running a little over time, but this is the last actual slide. Here we're just showing that because snow is a naturally layered system, we are looking at these sort of, at least to start, these sort of bilayered systems here, in which if we look at the interaction between these fingers and this layered system, we can start to see the formation of these sort of horizontal ice lens structures, which are also found in nature. Here's a close-up of it. But yeah, if you're interested in the work I presented, here's a QR code to our most recent paper that was published last month. Again, I'm tangentially working on lab experiments, but I haven't been able to present those yet. But yeah, I think I'll open it for questions because I'm a minute and a half over, and thank you for listening.
Great, thank you for that, Nathan. That was really interesting. Again, if anyone from the audience has a question, they can type them in and I can read them out. But I was going to start with maybe a naive question, but like in your simulations, you have the formation of these fingers. And so if I wanted to like upscale that work and kind of do it over a much larger region, is there a way to kind of average out the impact of that fingers, or would I need to have like a grid size that always creates fingers of that size? I'm not sure if that makes sense, but.
No, it totally does. And it is not by any means a naive question. Yeah. That's a whole, for me, that's a whole other monster to tackle. So part of this work is to, because we've obviously observed these sort of the impact of these preferential flow in snow in nature. And so with sort of existing really large scale hydrological models, a lot of them don't consider this process or have very, like a average sort of like effects of these, what the preferential flow might look like. So one of the sort of goals of this project is to get really better estimations of that for upscaling. I'm probably not a great person to ask of how you do that. I mean, I know there's many upscaling methods out there, but we are currently actively thinking about that. I am working on a project that's looking at sort of like tens of meter scale of these sort of very similar systems. And part of that is looking at the effects of preferential flow. And obviously we can't run a 10 meter by half meter wide simulation. It's just far too expensive. And so we're kind of sorting, some of this like before, so say looking at the degree of channelization or excuse me, sorry for flipping around, or like some sort of effective infiltration rate where you have this fingering process could be useful in that regard, but it's a bit out of my field, so yeah, I'm not going to claim to be an expert on that.
It's not an easy thing to do. And so do you think that depending on your porous medium and depending on the heterogeneity, those transitions that you showed are going to be like quite heavily influenced, or do you think the boundary between between the secondary fingers is going to remain kind of roughly at, what was it, 10 to the -4?
Yeah, so yeah, that's a very good point. This is based on one snow type, which so in the literature, really, there's for these unsaturated flow models, it requires you to have certain properties of what the forest media looks like. So average grain size diameter, the snow has a specific surface area, and then things like the contact angle, etc. And unfortunately, in snow, there aren't too many experimental records. There are some, and they're very good, but there's just very limited like snow types and those quantities that we want to model of those snow types. So I think there's only around 4. So like very fine to very coarse snow, there's only like 4 that we have a very substantial record of all of these properties. So like the water retention curve and everything. And so this is for one snow type. Which here it's fairly coarse snow, but of course, yeah, like the Peckley and Stefan number have thermodynamic quantities associated with them, and also geometric quantities like the length scale. And so, based on different grain sizes or different heterogeneities, we would expect very similar behavior, because we think we use physical arguments to why this upper right region exists and why this bottom right region exists. We think they still should be linear based on, this is linear in log space, of course. There should still be some threshold where you now have some reaction rate that's too high versus your flow rate, or this sort of compounding effect here. But yes, these actual numbers would change. Here we're presenting this for one snow type.
Great. That was really interesting. Thank you so much. I'm going to bring back both our speakers and just say a huge thank you to both of you for presenting today. Both of you had really interesting research, and it was a pleasure listening to both your talks. And then thank you to everyone watching, and we hope to see you for the 66th session, which is going to be February the 11th. So with that, a big thank you, and goodbye.
Thank you.